नहीं तुसी आखिरी 2 लेक्चर लाए नहीं मेरे ख्याल अच्छा मतलब what was the last thing we did? We have basically discussed the we have basically discussed the expression for the magnetic field due to various current distributions. What we started with was we first of all gave Biot-Savart law, Biot-Savart law you can say, which gives us the magnetic field due to a small current element, just as Coulomb's law gives us the electric field due to a point charge. I'm trying to correlate that. We went on to apply the principle of superposition or using integral calculus to obtain the electric field due to various charge distributions. Similarly, using Biot-Savart law, that is the expression for the magnetic field due to a small current element, we have used integral calculus to obtain the magnetic field due to an infinitely long wire, the field due to a ring at its center and at a point on its axis, and we have gone on to determine the magnetic field due to a solenoid, which is for which the magnetic field for any point well within the solenoid is a constant and is equal to mu naught Ni. And the magnetic field at one end of the solenoid is mu naught Ni by 2. Just as we use the Gauss theorem in electrostatics to determine the electric field due to certain complex charge distributions such as a line, a sheet, a sphere, insulator, conductor, hollow, solid. Okay? Similarly, we will use Amphere's circuital law to determine the magnetic field due to complex current distributions. That is the magnetic field due to a hollow wire, the magnetic field due to a solid cylindrical wire, the magnetic field due to a solenoid, due to a toroid, and so on. It means the lecture for today is Amphere's circuital law, ACL in short. Amphere's circuital law. The line integral of the magnetic field for a closed path. The line integral of the magnetic field for a closed path is mu naught times the net current threading the closed path, is mu naught times the net current threading the closed path. Sounds familiar? The surface integral of the electric field for a closed surface in air is 1 over epsilon naught times the net charge inside the closed surface. Now we have the line integral of the magnetic field for any closed path is mu naught times the net current threading the closed path. इधर अगर मैथमेटिक्स बनाइए तो ये क्लोज पाथ लाइन इंटीग्रल है. I hope it makes sense from symmetry. If surface integral of the electric field was E dot ds, the line integral of the electric field would be E dot ds. कोरिलेट बहुत कर रहा हूं मैं. Did you remember that I did not give you any genuine proof of Gauss theorem in electrostatics? दो तरीके से किया. एक का आपको थोड़ा मैथमेटिक्स नहीं समझ आया, जिसका मैथमेटिक्स अच्छी तरह समझ आया वो बहुत स्पेसिफिक था. What we did was we imagined the closed surface to be a sphere and imagined the point charge to be at its center. या फिर I had imagined any random closed surface and placed the charge anywhere, but then there was that trouble that integral of ds cos theta over 4 pi over r square is 4 pi radians. That seemed more genuine to me rather. Over here also, वो भी मैंने करवाया, आपकी किताब में नहीं दिया होगा. Over here also we will not give you any genuine proof of amphere circuital law, but its application is more important. But sometimes at this level, there is a question on the paper: state and prove ampere circuital law. So we will here use a specific current distribution and a specific closed path and prove ACL. फिर नोट में लिखवा दूंगा मैं कि ये generally repeat. ठीक है? Proof. Consider an infinitely long wire carrying current. Consider an infinitely long wire carrying current. Imagine a closed path of radius A and the wire at its axis. Okay? रुक के बनाना जरा. थ्रेडिंग का क्या मतलब है? I said threading. It is just like सुई में से धागा पिरो दिया. सुई में करंट है कि धागे में? धागे. The closed path is the eye of the needle. ठीक है? And that is why threading. Okay? So current threading the closed path of radius A is how much? I. And this is the closed path of radius A. I have taken a symmetrical distribution for which the magnetic field is equal in magnitude and tangential to the closed path at every point. ये बना लो और फिर बोले. देखा, मैंने कहा था रुक के बनाना. मैंने कहा था आदित्य रुक के बनाना. हर पास शो होना चाहिए. बहुत कम बच्चों ने, किसी ने भी नहीं किया. पावर लग गया. How many of you have has prepared electrostatics nicely? Okay, that is very good. Current भी? Current तो ठीक है. So फिर we will be on for a test. ठीक है? Before we really start into step 2, I told you I have divided this into 3 parts. We've covered part 1. ठीक है? Did I give you an assignment or something?
Yes.
What did I give you? अच्छा, उसमें तो अच्छी डिवीजन हो गए इसके आंसर्स थे आपके पास? चलो आंसर लिखते हैं इसके. So the magnetic field is equal in magnitude and tangential to the closed path at every point. The magnetic field is equal in magnitude and tangential to the closed path at every point. Line integral electric field का पता क्या मतलब था? कि if I divide this into छोटे-छोटे parts, तो B dot dl की वैल्यू क्या आती है? ये मतलब है line integral of the magnetic field का. Now right, the line integral of the magnetic field for the closed path. The line integral of the magnetic field for the closed path. The line integral of the magnetic field for the closed path. ये मतलब हुआ ना, हर पॉइंट पे बी और डीएल में एंगल 0 है. बी एंड डीएल विल बी एट द विल बिलोंग सेम लाइन एंड बी बाहर आ गया. बी कितना है? म्यू नॉट आई बाय 2 बाई ए. इंटीग्रल ऑफ डीएल कितना है? 2 बाई ए. Therefore integral of B dot dl is mu naught. देखो अरे पोटेंस में it means we have proved amphere circuital law by using a very specific kind of a situation. ठीक है? But it is true in general. Note. KCL is true in general. ये true के valid लिख लो. KCL is valid in general. That is for a closed path of any shape. And the wire can be threading the closed path. From any point. Example. path है. जरूरी नहीं है कि सेंटर में से जाएगा. It could also be ठीक है. और इंटरेस्टिंग बना इना विच b dot dl is b dot I. b dot dl is b dot I. हाँ देखने में बहुत अच्छा है. Clear? How much current is threading the loop? 2I. So integral of b dot dl will be 2I. Do it again. 3I. Interesting. Dr. Raj. If exact. This is what is true ampere circuital law. Its application part. Because the current I threads the loop in one sense and I in the opposite sense. Net current thread in the loop is 0. Threading the closed path is 0. Net current threading the closed path is 2I. These are the kind of applications that we are going to apply here and use to derive the expression for the magnetic field due to various current distributions. If you remember, the first thing that we did with Gauss theorem was we determined the electric field due to a point charge using Gauss theorem. We proved Gauss theorem using the electric field due to a point charge. Similarly, over here also, first of all, we will derive an expression for the magnetic field due to an infinitely long wire using ampere circuital law. If you remember, this expression was quite a tedious and a lengthy expression in which I divided it into 3 parts and then I asked you to substitute it back again. You can observe your article. You can observe your article using Biot-Savart law. Dekho. Using Biot-Savart law, we derived the expression for the magnetic field due to an infinitely long wire. Applications. पहली बात, magnetic field due to an infinitely long wire. Let me remind you of Gauss theorem and electrostatics. छापा की कितना सही कि we had 4 steps. अपने पास है क्या और करना क्या है. Then we observe that whether the electric field is tangential or not. आपने पढ़ा आपने? It is only the normal component of the electric field will contribute to the electric flux. We observed that and found the flux to be 0 for some surfaces and maximum for another. Those steps. Then we calculated the surface integral of the electric field actually, and then we applied Gauss theorem and we equated them. In a normal numerical, we simply used to do it by equating the two. यार ये किया हुआ है mathematically और ये Gauss theorem. Over here, it's the same. पहली बार. Consider an infinitely long wire carrying a current I. फटाफट समझ आएगा बड़ा अच्छा. काफी काम करवा दूंगा. Consider an infinitely long wire carrying a current I. We have to find the magnetic field. At a point, perpendicular distance A from the wire. We have to find the magnetic field at a point. We have to find. We're not going to use it. We have to find mu naught I by 2 pi r. Okay? So in these situations, we can always use symmetry. So we will imagine a closed path of radius r and the wire at its axis. Like at its center, at its axis. Imagine a closed path of radius r. Radius r is करके परपेंडिकुलर डिस्टेंस r ही कर लो बेटा. या इक्वल जो कर लिया ठीक. क्या लिखा था? a. Okay. We imagine a closed path of radius a. Comma. The wire at its axis. बड़ा आसान है. ये जो लिखा है वो इमेजिन कर लेते हैं. बी केयरफुल नाउ. यहां फील्ड निकालनी है. जहां फील्ड निकालनी है उत्थे एक ठीक है क्लोज पाथ इमेजिन कर लो ऑफ रेडियस ए. जिसने ए लिखा है ए कर लो, आर लिखा गलत पड़ी. अब देखना है किस पॉइंट पे फील्ड कैसे है. द मैग्नेटिक फील्ड इज इक्वल इन मैग्नीट्यूड एंड टेंजेंशियल टू द क्लोज पाथ एट एवरी पॉइंट. The magnetic field is equal in magnitude and tangential to the closed path at every point. डीएल सारे के ऊपर वेक्टर पाया करो, सिर्फ एल के ऊपर नहीं. मैंने बहुत स्टूडेंट्स देखे हैं यू पुट अ वेक्टर ओनली ऑन एल. उनकी स्टेप्स हैं अपने. वी विल फर्स्ट ऑफ ऑल कैलकुलेट द लाइन इंटीग्रल ऑफ द मैग्नेटिक फील्ड मैथमेटिकली एंड देन अप्लाई एसीएल एंड देन इक्वेट फर्दर. द लाइन इंटीग्रल ऑफ द मैग्नेटिक फील्ड फॉर द क्लोज्ड पाथ. द लाइन इंटीग्रल ऑफ द मैग्नेटिक फील्ड फॉर द क्लोज्ड पाथ. सिंगल स्टेप्स करते से याद है आपको ताकि वो आसान लगे. यूजिंग ACL कितना जी म्यू नॉट फ्रॉम 1 and 2. B into 2 by A is mu naught I, or B is mu naught I by 2 by A. बहुत आसान. Go and wash it. Don't rub it. The retina gets disturbed. The cornea. ठीक है जी. We are convinced that this is right. दूसरी बात, magnetic field due to a hollow cylindrical current carrying wire. Magnetic field due to a hollow cylindrical current carrying wire. Consider a hollow cylindrical wire carrying a current. Consider a hollow cylindrical wire of radius r. बड़ा r है. consider a hollow cylindrical wire. मत बना लो, बाद में मैं काट देता हूँ. हाँ जी. Infinitely long. We have to find. चलो पहले पकड़ लेते हैं. This is ready. Axis से distance r पे फील्ड निकालनी है. We will imagine a closed path of radius छोटा and the cylindrical wire at its axis. This looks better. Let's see. Okay? This is good. Our part नजर आ रहा है. So I think if I do the article orally with you, just a minute. जितने डिस्टेंस पे फील्ड निकालनी है, उतने डिस्टेंस के रेडियस का एक क्लोज पाथ अज्यूम कर लो with the cylindrical wire as its axis. First of all, we will determine the line integral of the magnetic field. It will be B into 2 pi r. Then we will use ACR. It will be mu naught I. Current I तो एक ही है ना, बाहर से जा रहा है. These are not two wires. This is a single wire. ठीक है? तो B is equal to mu naught I by 2 pi r. It means to determine the magnetic field for a point outside the wire, the entire cylindrical wire can be assumed to be a thin wire at its axis. ठीक है? लो जी, आर्टिकल बनाते हैं. कंसिडर, मैंने कहा था रुक के बनाया करो डायग्राम. Consider a hollow cylindrical wire of radius बड़ा r carrying a current I. We have to determine the magnetic field. We have to determine the magnetic field. At a point P outside the wire. That is at a distance small or greater than r. That is a distance small or greater than r from its axis. ठीक है? Imagine a closed path of radius r greater than r. Imagine a closed path of radius r greater than r. ਇੱਥੇ ਬਣਾਉਣਾ ਹੈ. field is equal in magnitude and tangential to the closed path at every point. The magnetic field is equal in magnitude and tangential to the closed path at every point. Tangential to the closed path at every point. बस एक बारी मैथमेटिकली निकालो लाइन इंटीग्रल, एक बारी इसे निकालो. The line integral of the magnetic field. The line integral of the magnetic field for the closed path. कितना हुआ? B dot dl is B dl cos 0. यहाँ भी शो कर देना B dl जो आ जाएगा B into 2 pi r using ACL. Mu naught I from 1 and 2 B into 2 pi r is mu naught I, or B is mu naught I by 2 pi r. For r equal to r, B is mu naught I by 2 pi r. उल्टा लिखा है, स्मॉल r equal to r है, क्योंकि करंट थ्रेडिंग तो उतना ही रहेगा, ये कोइंसाइड कर जाएगा क्लोज सरफेस उसके खुद के रेडियस से. केस 2, to find the magnetic field at a point inside the wire. To find the magnetic field at a point inside the hollow wire. What is the obvious answer? 0. Because a closed path of radius r less than r will not thread any current. So if this is the wire, what? ये ठीक है. This is the radius. Clearly, a closed path of radius r less than r does not thread any current. Clearly, a closed path of radius r less than r, a closed path of radius r less than r does not thread any current. Therefore, from ACL, integral of B dot dl is mu naught into 0. Therefore, B is equal to 0. Conclusion. D is equal to 0 for r less than r, and D is equal to mu naught I by 2 pi r. That is, D is inversely proportional to r for r greater than adversary. And if we try to represent it graphically, it is going to be something like this. इनवर्स प्रोपोर्शनैलिटी का ग्राफ कर्व्ड होता है, इनवर्सली स्क्वायर का भी कर्व्ड होता है, उसकी स्लोप ज्यादा होती है। सिंपल। Means the entire wire behaves like a thin wire at its axis. Good here. For r greater than f. For r greater than f, most equal to r. The hollow cylindrical wire behaves like a thin wire at its axis. The hollow cylindrical wire behaves like a thin wire at its axis. These holidays, I did not think that. I found the definition from physics. A beautiful expression, and I laughed my heart out. We're trying to make things very simple in physics. He says that physics is nothing more than a search for ultimate simplicity. Physics is nothing more but a search for ultimate simplicity. But so far what we have is an elegant mess. So far what we have is an elegant mess. We are trying to explain the magnetic fields of situations with just one thing, graph. And just at the moment when a student is beginning to understand the shape of the graphs, we start teaching them projectile motion and say this is the trajectory. So, actually, thinking we are trying to put things in a very concise and a simple form, but it actually really messes up things in somebody's mind. But if you really think and call it an elegant mess, look, the magnetic field due to a solid cylindrical wire. The magnetic field due to a solid cylindrical wire. Case wire. For a point inside the wire. Sorry. For a point outside the wire. Consider a solid cylindrical wire of radius r carrying a current I. ठीक है, ये सारी के थ्रू करंट है. The current is I. The current through the entire cross-sectional radius R is I. I hope you understand this. This entire cross-section, of radius R, and the current I. I think outside the wire, it won't have any difference. So you can repeat the article at home. You can leave as much space. एक आपकी प्रैक्टिस हो जाएगी. सारा पूरा लिखना है. रिद्धि, आधा बचता नहीं. तो मैं यही लिखवाऊंगा. ठीक है? Consider a solid cylindrical wire with radius r. We have to find the magnetic field at a point P outside the wire r greater than r. Imagine a closed path of radius r greater than r. The magnetic field is equal in magnitude and tangential to the closed path at every point. The line integral of the magnetic field for the closed path using ACL. ये सारा डिट्टो आ जाएगा. आपकी प्रैक्टिस हो जाएगी एक बारी. ठीक है? यही डायग्राम है और ये भी यही रहेगा. Let's come to case 2. Let's come to case 2. For a point inside the solid wire. सारे करंट आए. This is of radius r, but we have to find the field here. क्या करूं? Imagine a closed path of radius r less than r. ये एक्चुअली करंट, ये देखो, ये ऐसे बना सकते हो. ये सारा करंट आएगा. सारे में से करंट आएगा. इसको स्मॉल एरो से देखो, at an equal distance r less than r from the axis, the field will have the same value. At an equal distance r, the field will have the same value. That is why I imagined a closed path of radius r less than r. The field will be equal in magnitude at every point. Imagine a closed path of radius r less than r. भी करो ना पहले. Imagine a closed path of radius r less than r. First up, the field will be equal in magnitude at every point. The field will be equal in magnitude at every point. I think our first aim should be to determine the current threading the closed path of radius r less than r. It will obviously be less than r. जितना r बड़ा होता जाएगा पर less than r रहेगा, the current will go on increasing. But if you go outside, then the current threading remains the maximum. But let's come back here. Let us determine the current threading the closed path of radius r less than r. Let us determine the current threading the closed path of radius r less than r. I dash is equal to I over pi r square, this is the current density, into pi r square, which would be I r square by r square.
करंट डेंसिटी एरिया ऑफ क्रॉस सेक्शन के बेसिस पे देते हैं।
बेटे एरिया ऑफ क्रॉस सेक्शन से ही पता लगेगा ना कि इतने से, बिकॉज हर पॉइंट पे एरिया ऑफ क्रॉस सेक्शन उतना ही, करंट तो उतना ही रहता है।
एल में देते हैं।
L, बेटे current is the rate of flow of charge. We have to find the current threading the closed path, ये वाले closed path में से, तो वहां तक तो बात सेम ही रहेगी। The current threading the closed path of radius r, बड़ा r is I, but उसमें छोटा r कितना होगा? उससे कम नहीं होगा। So आपको अगर पूछा जाए कि ये पूरे सेक्शन में से तो r है, तो इतने में से कितना होगा? तो obviously the line integral of the magnetic field for the closed path. The line integral of the magnetic field for the closed path. B into 2 pi r. Using ACL. Mu, where mu would be the permeability of the medium inside, into I dash, which would be mu into I r square by r square. From 1 and 2 क्या है?
mu I r over 2 pi r
B into 2 pi r is mu into I r square over r square. B is mu into I into r over
2 r square.
2 pi r. Directly proportional to r. I think वही कहानी है यार, स्फीयर्स वाली। वहाँ पे चार्ज इंक्लूड बढ़ता रहता है, यहाँ पे करंट थ्रेडिंग बढ़ता रहता है। Conclusion. B is proportional to R for R less than R. B is inversely proportional to R for R greater than at most equal to R. And if we try to represent it simplicity, it goes something like this. It means whatever might be the shape of the wire, the magnetic field would be maximum at its surface. Magnetic field is the maximum at its surface. And for a point outside the wire, the entire wire behaves like a thin wire at its axis. तो जी काफी करवा दिया मैंने आपको। फिर बातें करते हैं, बैठेंगे बातें